Um, so I think you've listened to a few talks from some of my colleagues already today, but I work for um, Maya HCT, and so very briefly on the company. We're a software development and services company with strong roots in the space industry. So if any of you are familiar on the line with the brands TMG or Space Systems Thermal, so that's the thermal code that is developed by Maya. So that's going to feature a little bit in the presentation today, but it's more so related to some recent research that we've been doing into AI machine learning techniques for generating reduced order models. And so that's what I'm going to be talking about today. So very simple overview for the presentation. I'll go through a little bit of background. Then I wanted to review some of the reduced order model technology that's out there. Then look at the AI-powered ROM methodology that we've been researching and testing out. Then I will present some of the results that we've produced thus far, and then end with a conclusion. So somewhat self-evident, but based on the feedback that we receive from at least our colleagues and customers in the space industry, is that there is a need to accelerate and automate, make it easier, essentially, to generate reduced order models, make that process much easier. Because the goal is to be able to run the source models and ultimately the reduced order models faster. But there's an interesting need as well that comes out of the space industry, is that these reduced order models need to be somewhat based on the physics of the actual system that's being represented. And so that kind of shapes in a way the way that we can generate those reduced order models. What do reduced order models actually do? What purpose do they serve? Well, there are actually a number of them, and we've actually seen some uses of those in other talks, TFAWS this year. First and foremost, it's a way of sharing models or integration into system level 3D models. So being able to share your unit or payload models with your system integrators. Other uses are to be able to capture the behavior of these subsystems within a one-dimensional system level simulation, such as one that can be provided by AIMSIM or by Simulink or any of the other 1D MBSE tools out there. They provide the ability to explore your design space more quickly. So do trade studies by having a model that runs that much faster than your full-blown detailed model. You can use it to design and tune controllers by having a representative plant in the loop. And they can also be used for the democratization of CAE. So having a quick running model that's still based on the physics of the problem can be used to allow designers to actually perform analyses quickly and gauge their designs. So now just getting into some of the existing technology, and this is actually coming from some of our colleagues at Siemens who have developed a plugin to do to use a projection technique to prepare a reduced order model. So very often this technique involves some sort of linearization or an assumption that the system that you're using is linear. So you would take the example, the heat equation, which is a PDE, but then by discretizing it in space and essentially generating a finite difference model, it turns into, if the conductances are in the system are constant, it turns into a linear state space model, which you can then, using various methods like, in this case, Krylov subspace method, you can project the very high dimensional degree of freedom model onto a lower subspace, and by selecting specific areas of the model that are of interest, where the temperatures are of interest. And so this is the technique that is used by Siemens in their model order reduction plugin, which incidentally makes use of the TMG solver under the hood. So this is the little UI that they've built into the into SimCenter 3D in order to allow this model order reduction process to take place, and it actually produces a state space model that can be used in MATLAB or Simulink afterwards. It does assume that the model is linear. However, just recently we spoke with them, and they made it work with radiation as well. And so with our help, we're going to be hopefully evaluating how well it works on space-related models. Moving on to the more traditional, quote-unquote, traditional reduced order model technique. And it's certainly the one that we at Maya have employed in many of our thermal analysis consulting projects. It's to generate an equivalent reduced set of conductances and calculation points to capture the general behavior of your system. So if you're running, for example, a space system thermal or TMG model within SimCenter 3D, you can define a card called param_reduce, which identifies your reduced order calculation points, and then it will determine a reduced number of conductances between those calculation points. Now those conductances can be varying with time, obviously if you have a transient analysis, and they can also have time varying capacitances if the thermal behavior of the system depends on temperature varying with time. So one of the techniques we can use is an optimization tool like HEADS to optimize the conductance values to best fit the behavior of the full system model, and then by extension have a reduced order model that's, I guess, optimal to represent that behavior. And then that reduced order model of conductances and calculation points can then be incorporated into a system model as requested by, for example, the system integrator. So this is an example of I think it's a power control unit. We're obviously not showing the customer model. This is just the simple reduced order model. It had about 2.5 million elements in it, and we reduced it down to 18. Using that param_reduce technique, and then using SimCenter HEADS, the multidisciplinary optimization tool, we were able to try and find the best conductances to match the behavior of the full system model. And as shown in the transient analysis results in the bottom left, we're usually within 1 degree of the equivalent temperatures from the detailed model. So this is definitely one technique that's possible, but it is somewhat hands-on to define all the reduced order groups, and then you have to do an optimization loop in order to achieve this. Another technique is surrogate modeling. We've seen a number of examples of that at TFAWS this year. So that's the ability to run a design of experiments within the full parameter space of your detailed model, and then extract a response hypersurface or response surface model that best fits the data that you get from running your detailed model a number of times. And so there are different interpolation methods that can be used, Gaussian curve fitting, kriging methods, radial basis functions. And what this does, get basically a response surface model that maps the input parameters that you provide it to a specific output response, or a number of output responses, because you can do this with a number of responses that you're interested in. And then how can you use this surrogate model? Well, it can be used in further design space exploration. It could be used in a designer-facing app, or it could be used in controller design. The one thing to realize that typically this method is used for static models, so steady state models where you're mapping a fixed set of input parameters to a fixed set of output parameters. But there are ways to adapt this to dynamic responses, and this is an example of some attempts that we did to do exactly that, leveraging principal transient response extraction. So this is an application of a theory called proper orthogonal decomposition. If you have a number of test training cases of transient responses, what you can do is you can extract the dominant modes of that collection of transient responses and then generate a surrogate model that determines the coefficients on those different modes for a given set of input parameters. And then you can generate a new transient response by linearly combining those modes with the predicted output coefficients. So we tried that out using a very simple satellite model. It's a tutorial model that we built in SimCenter Space Systems Thermal. It includes radiation in the orbital environment. On the right-hand side, you see a plot where all the black dots represent time averaged temperature responses from actual training runs. And then the color contour behind the scenes is actually a map of the difference in the predicted response versus what was actually obtained from the actual run. So the predicted was produced by this method. We actually are using a leave one out cross-validation methodology here, where we take the point we want to test, eliminate it from our training set, and use all the other training sets which are in the vicinity of it within the design space, and then train a surrogate model with the proper orthogonal decomposition to predict what we would actually produce at that specific point. And for the most part, we're within a good agreement, though there are some areas where the error becomes a little bit more significant. If you look in the bottom left, the red dot in the middle actually represents the prediction of the transient response that we got at one of the reduced order elements, the response with time. So that is kind of a survey of some of the different technologies. I want to talk about now the AI-powered model technique. So you can kind of see the graphic here. Similar idea, but the goal here is to kind of bolster the predictive capability of the reduced order model under more arbitrary conditions, and in particular, when we're talking about transient responses. So what we end up doing is, again, take our detailed model, the toaster, jokingly, and generate a whole bunch of training data from a number of, again, transient simulations. And then actually produce a training model, machine learning model that's going to predict at every time step a condition for the model that's going to allow us to iterate and predict the temperature at the next step. I'll come back to that in a second, but you'll see it represented better in an upcoming slide. But the whole goal is to be able to have something that operates under more arbitrary conditions, and that can also be used in transient 3D system simulations. So what's kind of new about our approach? In a sense, it's a hybrid approach. We're combining the machine learning to predict the arrangement of thermal connections within the reduced order model, but then using those thermal connections to actually calculate the next set of temperatures as we would in the thermal solver itself. So it's not necessarily a black box. The solution can evolve, not unlike the previous ROM methodology that I showed. The conductances aren't fixed. They can vary with time. And then also the idea is, unlike a surrogate model, we want to be able to include it in the system 3D model so it can be influenced by external heat loads. And yeah, also unlike the surrogate model, it's not a single best fit, but something that can be time dependent. So digging a little bit deeper, we would still use the reduced group methodology that I described before to generate what we would call an input file reduced that has a time history of all the temperatures for our reduced groups, but also a time history of all the thermal connections and heat flows in the detailed model. And then we would parse all that training data and put it into a more well-formatted table of training data on which we can then train a regression or machine learning model that will then be used inside of the thermal solver to predict those temperatures, as I was saying before. So currently we're using our own solver, the TMG solver, also known as SimCenter Space Systems Thermal. But conceivably, it could be used with other thermal codes as well, like CINDA or ECTAN, because it's a matter of extracting the equivalent heat flows, inductances, and capacitances for the model. So if that data is available, we could adapt this to the same methodology. And then the regression model, the machine learning model, we've tried deep neural networks. They didn't perform as well, potentially because we didn't try it with a significant amount of data points on which they rely. But we had some reasonably good results when we used support vector regression. And these will be the results that we show in the results section in this presentation. Yeah, and as I said, the reduced TMG model that's leveraging the machine learning algorithm allows the system model to predict the next temperatures. And this is being accomplished by a user subroutine, which actually calls this predictor executable, which is a separate executable that houses the machine learning algorithm. So I'm just looking at my time. I want to leave a little bit of room for questions, so I'm going to accelerate through these results. So here are a few of them. This is an example PCU model. It has about, I think it's 3 million elements, so a fairly detailed model. I think this is a redacted model. We tried it on a customer model, but I can't actually show it here. But it gives you an idea of 10 card trays within 10 cards within a card tray. And in this example, we're using the SVR regression method. So the training data that we provided to the training of this ML model was 10 different variable nonlinear heat loads applied to the different cards in the PCU. And then the test solution was, first of all, a linear model that varies within the range of the heat flows of the training data. So we apply this test linear heat load to the 10 boards. And the results that we get when we implement this AI algorithm is actually pretty interesting. So with just 2 training solutions, mind you, they are transient training solutions, so they produce a lot of data. We're able to predict, as shown on the screen, fairly well the temperature response of a few of the cards that we're showing here on the screen. So the black dots are the predicted temperature, while the blue dot is what would actually have been predicted by the fully detailed PCU model. So the next thing that we wanted to try, though, is with something a little bit more complicated, a nonlinear heat load applied to the 10 PCB boards or cards in the PCU. So this is again within the range of heat flows, but it's definitely not following the same sinusoidal test pattern that our training pattern that we threw at the model. And so the predicted temperatures don't match quite as well the actual exact temperatures. So the results on the top line are when we provided with 2 training solutions. When we provided with 4 training solutions, it doesn't significantly improve the temperature prediction either. So we needed to dig a little bit further into why that's the case. And it actually has to do with some of the heat flow that is leaving the box to the environment in this test case. So for one of the boards, or sorry, one of the surfaces, I should say, of the PCU, the heat flow of the test case, which is shown in with the dark blue dots, is well within the range of heat flows that were within the training data. But for another one of the surfaces of the PCU, the heat flow of the test case is not within that range. So that suggests that we're not fully covering the this training space, or the training space is not sufficiently covering the space that could be encountered by the reduced order model. So it suggests that more training data might actually be necessary for this case. So here's a customer PCU model. Again, same order of number of elements, 2.7 million. The runtime for this model is 1.5 hours. Again, we use the SVR method, and we threw at this two training solutions, the top red sinusoidal heat load and the bottom green heat load, and the test solution we put right in the middle. So it's not varying that significantly away from the training data, but it's still different. And we wanted to see whether on actually a real model we'd be able to predict the temperatures well with our ROM. And so here are the response temperatures for the various boards within the PCU. And it actually turns out that with the AI-driven reduced order model, we're predicting the temperatures pretty well. And I guess the key thing is, instead of 1.5 hours, the runtime was 2 minutes. And this is with the reduced order model actually within the context of a larger space systems thermal run, like not by itself. So the actual calculation just of this is quicker, but you also have to keep in mind that it's calculating temperatures of the environment at the same time. So this is quite interesting. So it suggests that the reduced runtime compared to the full model is quite interesting for an AI-powered ROM. It's definitely suitable for transient simulation, in contrast to the best fit conductance models of the traditional way of generating a ROM, or with surrogate models. This AI-powered ROM can accurately predict time-dependent conductances, heat loads, and temperatures. So it would be suitable for monitoring or process control, and would be capable of dealing with complex time-varying boundary conditions. But in terms of next steps, we want to try this on more varied conditions and make sure that the data collection requirements for this are not so demanding to produce a reasonable reduced order model. But all in all, the research is promising. We look forward to continuing it. So I think that's it. Yep. So at that point, answer a few questions. I don't actually have view of the chat window here, so I guess, Glenn, if there are any questions, I'd be happy to answer.
Hey, Christopher, this is Glenn. So you're the new product development director at Maya Heat Transfer Technologies?
Not product development manager. We have product managers specifically, and one of my colleagues, the authors here, is the product manager for our TMG space system thermal solver. But I'm more involved in new product development, so exploring new technologies like the one we have here, and some of the other initiatives that we have at Maya. So yeah, related, but not quite the same.
Thanks for that. Yeah. Do you have any comments about any new technologies that you're evaluating?
Sure. Well, certainly we're getting deeper into machine learning techniques, particularly when it comes to industrial applications, Internet of Things. We've been looking at technology for AI-powered virtual sensors to predict conditions within systems that cannot be fully instrumented. So leveraging what you can instrument and feeding them through a machine learning model to predict the things that you can't actively measure. That's an interesting topic. We're looking at correlating thermal math models to experimental data, more efficient ways of doing that, both for spacecraft applications, but also in the aero engines industries. I think that's mostly what I can talk about right now, but those are some of the flavors of things that we're looking at.
Excellent. Great presentation. I'm just going to check real quick online to see if we have any. I'm not seeing any. Thank you very much.
I'm the last one of the day, so people are probably heading out.